Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What's new in the world of science?
Well, this is a story about detecting explosives. Now, the traditional way of doing this is with really cute dogs.
Yep.
Yeah, so things like Springer Spaniels, really excited. You spend years and years training them up to associate the smell of explosive with food, and they get really good at it. And, I mean, dogs' noses are incredibly sensitive things.
Yeah.
The problem is, of course, it's really expensive to do this. And
it's dangerous for the dogs too.
Quite dangerous for dogs, and they can get distracted by food and all sorts of other things. So people have been trying to make artificial noses for a long time.
Artificial noses?
Artificial noses.
Right.
They've already got explosive detectors, which you probably might have seen in the airport recently. They sometimes swab some of your clothing and put them in a special machine. These are kind of great big machines, and they tend to work by separating out different molecules in the gases evaporating off your clothing, and if they detect any of them are explosives, and they sort of apply an electric field to them, and different molecules move at different speeds, and if any of them go to the right speed for explosives, then they'll sign up that you might be dangerous. But these are quite big and not very convenient. They take quite a long time to take measurements, so people have been trying to make artificial noses because noses are really quick. And a group in Israel, they've got to about as good as a dog's nose so far, but a group in Israel has just come up with one which is about 1,000 times better than a dog's nose.
Wow. They've
made little tiny wires out of silicon on a chip, and they've covered them with a chemical, amine type chemical, with little receptors on it which grab a particular type of explosive molecule. And then, so if any molecules come across, they come off and grab onto this wire. That affects its conductivity, and so you can detect that with some electronics, and it gives a result within seconds. At the moment, it will detect, a dog can do about 1 part in a billion, so 1 molecule of scent in a billion molecules of air. They reckon this can do 1 part in a trillion. It's not quite so good with air, but if you can get the molecules inside a liquid, then it will detect 1 part in a trillion, which is really, really impressive. So they're attempting to build haven't got a kind of actual device you can buy off the shelf yet, but they're attempting to sort of combine it with some little fluids devices, so it will kind of pump air through some water, then pump it past their sensors, and hopefully it will find the explosives really quite efficiently.
Artificial noses, whatever next. Anyway, let's get on to our first questions. Mike in Colchester says that he gets the most amazing pictures on his television from space, which got him thinking, how much power do the satellites have to generate to give me these amazing pictures, and where do they get the power from?
They basically, satellites, there's no power stations, you can't plug them into the wall, so they have to get the power in a way which is something which is coming past you, and what they use is sunlight. They've basically got solar panels on them. The amount of power which they use in total is really quite limited, because there's a limit. I mean, there's a limit to how big a solar panels they can put up there, and the solar panels can only pick up, there's about 1 kilowatt of light hitting every square metre. Solar panels maybe 10-20% efficient, so it's you're probably only getting about 100 watts, maybe 200 if you use very expensive solar cells per square metre, and the limit to the amount of solar panels they use. So the amount of power they're using is around about 1, 2, 3, possibly for a big one 4 or 5 kilowatts. So 2 or 3 kettles. That can spread out over the whole of Europe, is really not very much power, but that's the reason why you've got to use quite a big dish, so very, very directional aerial and very, very good electronics to pick up this signal. So you can get good pictures even from this minute signal from a satellite about 36,000 miles away in space.
Gosh. To the email now, Michael has sent one in saying that, I can't pronounce your other name, Michael, I think it's Summersky. What happens to the speed of light, Dr. Dave, when it passes into and out of glass?
Well, basically, light is a wave, an electromagnetic wave, and in space it's just interacting with the vacuum, and the speed it happens to travel at is about 300,000 kilometres a second. In glass, there's lots of electrons in there, mostly it's the electrons it interacts with, and that slows it down, and so the wave still carries on, but maybe sort of 200,000 kilometres a second, 150,000 kilometres a second, so really fast, but significantly slower. It's actually this slowing down which causes refraction, so the bending of light when it enters a substance. So if you ever looked at a pencil in a glass of water, it looks bent. Yeah. And that's because light is bending when it enters and leaves the water, because it's speeding up and slowing down. And then when it leaves again, there's no electrons to interact with again, it's just interacting with the vacuum, and it carries on at the speed of light in a vacuum, so it carries on at 300,000 kilometres a second.
All right, well, on the Twitter page, and what's the address of your Twitter page? Is it just Naked Scientist?
Naked Scientist, yeah.
At Naked Scientist. Alfie Stopani, why do onions make your eyes water?
Very good question. I suffer from this horribly. I hate cutting onions. Inside the onion, there's basically organic acids. That's called sulfenic acids. They're kind of big, complicated organic molecule. And when the onion's cut open and cells are damaged, it reacts with an enzyme to create a gas called syn-propan ethyl S oxide, if it makes it any good, which evaporates from the onion, gets into your eyes, and it triggers sensory neurons like pain and just basically creates pain directly to the pain sensors. I'm guessing it's evolved as a way of protecting the onion from being eaten by animals, because onions have got lots and lots of lovely sugar in them. And if it wasn't for all these sort of defence mechanisms, everyone would come and eat them. But because they can cause pain to the animals which try and do so, they probably will go and eat the tomato instead.
Let's go to the phones now, because it's time to have a phone question. We've got Mark on the line. Hello, Mark.
Hello, Sue.
Hiya. What's your question?
Question is, Dr. Dave, I remember you were saying that the moon was part of the Earth at one time. There was a massive impact.
Yeah.
And it got blasted off. Why is it not just a fragment? And why do the planets that we see are such these beautiful spheres that we see? Like, I mean, we know that we've got mountains and lakes.
But I mean, even considering that, the Earth is actually, if you scaled the Earth down to the size of a billiard ball or a snooker ball, it would actually be smoother than the snooker ball.
Cool.
So what we think are giant mountains compared to the size of the Earth are absolutely tiny. It's also with gravity. Because every object with mass attracts every other object with mass, and the bigger it is, the stronger these forces get. And so if you imagine if the Earth was made out of water, all the water is going to kind of attempt to get as close to the other water as possible. Yeah. And the shape which does that best is a sphere. So the water would flow until it created a sphere. Now, although to you and me a rock looks like a very hard thing, especially if you heat it up a bit, actually it will flow. So over millions of years, rocks will flow, especially if they're hot. And so the mantle below the crust of the Earth, which is only up to 20 or 30 kilometres thick, below that, the mantle, although you could hit it with a hammer, but if you leave it a million years, it will flow very, very slowly. So if you build a big pile, if you put a load of ice on Scandinavia, for example, the Earth is actually deformed and the mantle flows out of the way. Now, since the Ice Age, all that ice has melted, all the mantle is flowing back in to take that space where all the ice had pushed it down. And so Scandinavia and Skysing and down in southern England we're sinking very slowly because of this effect. And so when the moon was created, there was this huge impact. You got lots of incredibly hot rock spraying out. I think it fairly quickly accumulated into one big lump because it was essentially molten. It kind of then flowed as close to the other rock as it could get, which is a sphere. And so the moon's a sphere.
All right, thanks, Mark. Bye-bye, sweetie.
Bye-bye, Dr. Dave.
Bye-bye. Bye-bye. Right, our next question also comes through, via Twitter, actually. If you compress anything enough, will it become a solid? That's from Diving Duncan.
As far as I know, yes. The thing which I'd be least expect to become a solid, and doesn't even become a solid if you cool it down to absolute zero, so minus 273.17 degrees centigrade, is helium. But if you apply enough pressure even to helium, it does turn into a solid, basically because if you've got a load of atoms or molecules, if you push on them, if you keep pushing them together, they've got to get closer and closer together, and eventually with enough pressure, they just they lock into each other and they can't move past one another. The forces are required are too big, and they do essentially form a solid. So I think the simple answer is yes, although the pressures required are absolutely immense.
Let's go this time to Mike in Colchester, who says, "Hi, Jean. I am flying to Singapore soon. How lucky you are. How on earth do they get all those toilets to work, and where does all the waste go?" Dave?
I think certainly originally the toilets in planes used to dump it out of the back of the plane because carrying liquid around was expensive and they hoped they didn't hit anyone underneath. But I think now that millions and millions of people are flying around in planes, essentially they have big tanks in the aeroplane. The tanks are kept at the same pressure as outside. Mm-hmm. So if you ever flushed a toilet in a plane, you'll notice there's a very violent sucking noise. It's because the waste tank is at the air pressure outside, you're at 30,000 feet. So when you open the valve, air rushes very quickly through the valve into the waste tank, taking all the deposits with it very quickly. And to save weight, of course, they use very little liquids. But yeah, I mean, basically it all just goes into a tank, which doesn't actually increase the total weight of the plane, of course, because it's only stuff which was inside you to start with. So as the tank gets heavier, you get lighter. And then when they get to an airport, they empty it.
Right, we always get down to the nitty-gritty of things. A little note here from Mike. Dave, is it an urban myth that if you press the flush button on an aeroplane toilet while sitting on the loo, this vacuum effect has the power to make you stick to the seat?
The pressure difference, if it was sealed, could certainly stick you to the seat. I mean, you're probably talking about half an atmosphere, which is actually really quite a large pressure. But the problem is sealing really well. I think it'd be unlikely to be able to get a really good seal all the way around the seat. And of course, the seat is up over the top of the bowl, so there's a gap between the seat and the bowl.
Yeah.
So there's always going to be a gap there, so air can always get in there. So you might be attracted to the seat, but you're not actually going to seal anything, so you're probably going to be all right.
Lovely. Thank you very much. All right, let's go to this one here. Graham Hamilton says, when charging an electric toothbrush or mobile phone, when the device is fully charged, does it stop using electricity? In other words, is it okay or wasteful to leave it plugged in permanently, please? They go all hot, don't they? Dave?
It will slightly depend on the type of your charger. It will certainly waste some energy, especially the older, just straight, the heavy ones, which are actually just a straight transformer in there. Mm-hmm. They'll waste sort of less than a watt, sort of half or a third of a watt. They'll use less power than if they were charging your phone, but they will waste a little bit of power. The more modern ones waste less, but again will waste a certain amount. But as Professor Mackay, David Mackay, who's at the university, he did some experiments on this, and he got like about 16 chargers and put them all in at once and plugged them into the wall. And it still was less than a watt. And essentially, if you've got a certain amount of effort you're going to use in attempting to reduce your energy use the effort which you would have been spent turning off your phone chargers and use it to walk to the shops once rather than driving, and you'll save far more energy.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Let's go to the phones and say a very good evening to Robin. Hello, Robin.
Hello.
What's your question?
I've got a collection of shells. Most of them are very thick-skinned. And I wondered if this was because of the great depths and the pressure of water, rather like a submarine.
Yeah, you've got a huge amount of water above your head, its head or above its shell, so it's applying a huge pressure onto the shell. I don't think that's a major effect because, apart from anything else, the shells are essentially open at one end, most of them, and that's just filled with kind of soft, squishy bits. And so all the large pressure is going to do is slightly compress the body of the creature, which will compress all the way through the shell, and so basically the pressure inside the shell will be exactly the same as outside, or very close to the same as outside. It's a bit like if you go scuba diving. If you attempt to breathe even just 2 metres underwater through a pipe up to the atmosphere, so your lungs are full of atmospheric pressure air, it's incredibly difficult to breathe because you're attempting to breathe in against the pressure of the water. But if you go scuba diving, because the air you're breathing in is pressurised, the pressure on the inside of your lungs is exactly the same as outside, so you can go down tens of metres as long as the pressure is equalised between the two. I think the reason why the creatures have such strong shells is to resist other creatures trying to eat them. And if you've got a really big, thick, strong shell, creatures which have got to eat you have got to be much bigger and much rarer.
How's that, Robin?
Thank you.
You're very welcome. Now, Andy in Huntingdon says, can you explain how a night sight for a pair of binoculars works?
There's various different ways of doing them, but I'm guessing you're talking about the image intensifiers. Normally these look sort of green. There's, again, various technologies on these. The slightly older-fashioned ones, which are normally green, they work by... basically you have a camera type arrangement which projects light onto a screen.
Yep.
This screen is made out of a metal, something like sodium, which electrons can escape very easily from. And behind that screen you've got a vacuum, or a very low pressure gas, with about 1,000 volts across it to another screen at the back. So when the light hits the front screen, it knocks a few electrons off. Those electrons fly up this huge voltage towards the other screen. As they do it, they bash into a few gas molecules, knocking off more electrons. So one electron knocked off at the front turns into maybe 1,000 at the back. They're moving really quite fast. They've got lots of energy. Then they hit the screen at the back, and then that hits a phosphor, like in the front of your TV. So the electrons hit, or in front of an old TV. So the electrons hit the phosphor, create lots of light. So maybe one photon coming in could make 1,000 or 2,000 photons coming out. And so it's 1,000 times brighter, so you can see it only in starlight. The more modern ones, which the US military are using, basically just have a very, very sensitive camera, because you can make CCD cameras, like in a digital camera, sensitive enough to work under just starlight. There are also other versions which, instead of working on visible light and near-infrared light like all those do, they work on thermal infrared. So these are thermal imaging cameras you sometimes see on helicopters. And this is the far infrared, the thermal infrared, and anything at room temperature is glowing in this kind of light. So we'd be glowing really brightly, especially if you're hot. And so you can see anyone who is warm, any warm vehicles, just show up really brightly, even at night, because they're glowing, whatever the amount of light.
Interesting stuff.
Outside.
Andy has sent an email in saying, would it be possible or beneficial to make a liquid crystal display touchscreen keyboard?
So I think he's wanting to make a keyboard which is really easy to clean. So you just get a kind of, essentially something very like one of these modern phone touch screens. Yeah. So I think he's suggesting make a really nice, easy wipe screen keyboard. And you just sort of make an LCD so you can see all the keys and you can type on them. In fact, very like the keyboards you get on sort of mobile phones and things like and tablet PCs, tablet computers. Yes, it works. I mean, it works on a modern smartphone. It's just quite difficult to type on. Because the advantage of a real keyboard is you can find the keys with your fingers, and you know where all the keys are. And so you can type very quickly, and it's a bit like playing a piano. You can kind of learn where all the keys are. Whereas I think with a LCD sort of keyboard like you get on phones, I certainly have to spend a lot of time looking at it to work out where the keys are, because you can't feel them. So it's a lot slower. So you certainly could, and they are used, but I think there's disadvantages with it.
All right. And Mike in Colchester has said, is Dr. Dave's brain, is it the same size as it would have been 500 years ago?
Yeah, that's a good question. Obviously, my brain is an awful lot bigger than it was 500 years ago because I didn't exist. But that's a rather stupid answer to the question. Have people's brains changed in the last 500 years? I don't think so significantly. Possibly they're slightly bigger than they were, not really because of any genetic changes, but just because we're fed a lot better, in the same way that people have got taller in the last 50 or 60 years because we're getting a lot better nutrition, if anything slightly too good nutrition, so we're growing as big as our genes will let us, rather than being stunted. Because a lot of people 50, 100 years ago the reason why they were a lot shorter was because they just weren't getting enough food and they stunted their growth. And I wouldn't be surprised if that had a similar effect on the brain, but I don't know any particular effect.
Now, Dominic P6 has said, if you go the speed of light around the world for a day, a week goes by on Earth. Would people on Earth see you at a seventh of that speed?
I think the way the universe seems to work is that if anybody going at any speed anywhere in the universe looks at a beam of light, they see it as going at the speed of light, so at 300,000 kilometres a second. Mm-hmm. So even if two people are travelling at 1 million miles an hour relative to one another, or 1 million kilometres a second relative to one another, they both see the light beam travelling between them going at exactly the same speed. Everything else changes to make that work. So time changes, so that was the time dilation effect he was talking about, and space gets distorted, and everything else changes, but the speed of light always appears the same. It's absolutely bonkers.
Yeah, I guess
all
you've lost
the experiments that anyone has done. I mean, it's just kind of, as far as we know, that's just a fact of the universe, that the speed of light is always constant and everything else seems to change to make up for that. If you're actually going at the speed of light, time dilation is actually infinite, so no time passes for you if you were going at the speed of light. And so if you're going at the speed of light around the Earth for what appeared like a week to everyone else, to you it would appear instantaneous.
Bizarre. Ray and Whittam, is it possible to dig a hole from this country to Australia through the Earth? And if so, how long would it take? That'll keep you busy, Dave.
I think, theoretically, if you're talking completely simple physics, there's no there's no fundamental physical reason why you couldn't, or there's a huge number of practical reasons why you couldn't. The big problem, as I was saying earlier, is that when you get to great depths, you get into the mantle. Whilst it kind of seems solid if you hit it with a hammer, the rocks will flow. They're also at an immense temperature. They're sort of thousands of degrees centigrade, but the biggest problem is that the pressures are completely ridiculous. The pressure at the bottom of the ocean is very, very large, but because the density of the Earth is about 5 times that of water on average, every time you go down 2 metres, the pressure will increase by an atmosphere. So if you go down a kilometre, the pressure is going to be, if you go down a kilometre, 500 atmospheres. If you go down 10 kilometres, 5,000 atmospheres. 100 kilometres, 50,000 atmospheres. And building a tunnel which could support those kind of pressures and those temperatures would be just incredibly difficult and obscenely expensive, and fundamentally it's a lot easier and cheaper to fly.
Pretty has said, why can't we light a 100-watt bulb with a 1.5 battery?
1.5 volt battery, yeah. Sort of a normal battery. If you plug that into a 100-watt bulb, why doesn't it work? There's a variety of reasons for this. The first one is that a 100-watt bulb is designed to work at 240 volts. Mm-hmm. So for it to produce 100 watts of power, you have to connect it to a power supply which is pushing electricity through with a measure of how hard the pressure of electricity is volts, with a pressure of about 240 volts. If you connect a 1.5 volt battery to that, the current which goes through it is going to be about 130th of what you would get from the proper light bulb, and the power given out is going to be that 130th squared, so 10,000th, so it doesn't get nearly hot enough to light up. Mm-hmm. The second question is, could you design a different 100-watt bulb to connect to power off a 1.5 volt battery? If you had a really, really big 1.5 battery and you connected hundreds and hundreds of 1.5 volt batteries in parallel, and you had a very, very low resistance light bulb, you could put, for 100 watts, you'd have to put through about 60 amps of electricity at 1.5 volts, and you could produce a 100-watt light bulb. It would be kind of difficult, and 60 amps is an awful lot of current. You need huge copper wires going into it, and it'd be very difficult, but it would be possible. Could you do it with just a single 1.5 volt battery? The answer is no, because there's too much resistance in one of those batteries, and the maximum current they can probably produce is 5-10 amps, not a couple of hundred. So you couldn't get enough power out of a small battery.
One here that has come through from Michael in Kings Lynn, and I don't know whether Dave, whether you're going to know this or not, but he says, if a person was born blind, as they grow up, can people get through to them what seeing is?
I don't know. I guess you'd have to ask someone who's blind. There have been some interesting cases of people who were blind all their life. Then the reason why they were blind could be surgically removed. So if for some reason they had some kind of skin layer inside their eye and someone could remove it, all of a sudden they could see. Then their eyes work and they get the signals to their brain. And actually it's incredibly, incredibly confusing. Because when we're young, we learn how to see, and we learn how objects relate to one another, and we know what it means for an object to be in front of one another, and we learn how to recognise faces, and there's a huge number of things which we learn when we're very young, and they're kind of hard-coded in, and we don't have to think about them at all. There's quite a famous story, I can't remember the person involved, who had this done to him. In fact, the guy studying was quite a famous psychologist called Richard Gregory. He'd been blind all his life, and he couldn't understand what he was seeing unless he could feel it. Yeah. So he was fascinated with making things, and he went to see a lathe because he'd never seen a lathe. He never quite understood how it goes together. And when he went and looked at it, all he could see was kind of a load of different areas of light and dark and shade and lots of lines, and he couldn't put it all together as an object in his brain until he felt it. Then he could kind of relate the pictures he was seeing to the model in his head. Of what a lathe was, and so he could put it all together. So I think from that, seeing is people who actually can see after not having seen when they were kids find it very difficult to see. I think just explaining it to them would be very, very difficult.
What happens to a particle of light as it's leaving the sun, and why does it take so long to do this? This is from Tex the Elephant.
I think this is the story that it takes about 1 million years for light to get out of the centre of the sun.
Yeah, it goes back to from Fort Worth in Texas. Said you said on the show that it takes 1 million years for a particle of light to exit the sun. What is it doing for that 1 million years, and why does it take so long? And how do you know this to be true? How do you know, Dr. Dave? Come on.
Okay, I mean, people haven't gone and followed a particle of light all the way out of the sun because we haven't been thinking about those kind of questions for 1 million years apart from anything else, and we can't get into the sun and there's all sorts of reasons. So it's out of a whole lot of modelling. And it's not strictly the same particle of light which is taking 1 million years to get out of the sun. So what the result of that, what the calculation which someone has done to get that figure is that if you produce some light in the centre of the sun, it will fly a certain distance and it will hit an atom or probably an electron inside the sun. It will get absorbed by the electron and then possibly bounced off or re-emitted in another direction. And so this light can only travel micrometers before it hits another electron and bounces off. And so it's going to sort of take this what's called a random walk. It will bounce around the sun at random. And if you imagine that it was the same particle of light, in fact, it's probably got absorbed and re-emitted billions of times in this period. If it was all just one particle of light and it was bouncing around, the distance it would travel would be 1 million light years before it actually got out to the surface of the sun. And that's a kind of strange calculation, but it's actually very important for measuring how long it takes for something to change in the centre of the sun to get out to the outside. So if the core of the sun got a bit hotter, how long would it take for the heat to get out to the surface of the sun? And that's basically how long would it take for light, because the light's the way that most of the energy is transported around the sun, to get out to the surface. And that's about 1 million years.
All right, we've got time for one more question, and that has come in by email again, and this is from Michael Hunter, who says, does a magnetic field require energy, and if so, where does that energy come from?
It's an interesting question. For a magnetic field to keep on going, you don't need any energy at all, but to create the magnetic field, then you do need energy. So, for example, in a lump of iron, there's lots and lots of little magnets in there. Each of the atoms is a tiny magnet, and they form into little domains. And normally in a lump of iron, they're all pointing in random directions. But to create a large magnetic field, you've got to line those all up and stop them pointing in random directions. And that does take quite a lot of energy. In the case of a magnet, you put that energy in by using external magnet. So you either get a permanent magnet and push it towards the iron, which will take you away from the iron, which takes some energy, or you have to apply an electromagnet, which again uses some energy. And so creating the magnetic field uses energy, but once it's created, it doesn't use any energy to keep it going.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.